All right, my mathletes, here we go. We've got, last week we were talking about combinations and the formulas for that. Now we're going to just talk about the difference between a combination and a permutation. They are different. They have slightly different formulas. So let's take a look at what the difference is. So in a combination of items like we did last time, the order of the things that you pick doesn't matter. So for instance, if you're taking items A, B, C, and D, if you pick two of those items, A and B are the same as B and A. So you don't double count that because you're just looking for subgroups of the first group. So one of these numbers here is you dividing out those, what's the word for it? Those, I can't think of words this morning. Those possibilities that are repeated. This is dividing out the repeated possibilities here. So AB is the same as BA. So half of my possibilities are not going to be possible. Wow, that's a lot of possible. You know what I'm talking about. It's early in the morning, sorry. So another way to write our formula, we said, is if you have the combination, you can do it like this. I think that on your stretch, the combination of permutation stretch, it uses this notation here. You might also see it as combination of, four things, geez. And then you're picking two, so it might also look like that. But we said that the formula for this, where n was the number of things, so if you have the combination of n number of things and you're picking r different things, then the formula was simply n factorial divided by r factorial. Remember, that is where we're taking out all these combinations that were repeated because order doesn't matter. And then we also do n minus r factorial. So we explained it as n factorial things, so the total number of items, that's 4. The things that you are picking, there were 2 things we were picking, and then things that you're not picking. Because you can order the things that you're not picking a whole bunch of ways and they don't matter because you're not picking them. All right, and now we get to permutation of items. Permutation is when you pick things from a group, the order does matter. So you have a different outcome than a combination. So if you had a permutation, you're going to actually always have more outcomes than if it were a combination. So in a permutation, we're not going to divide by this number because this number was where it was A, B, and BA, and those are repeated, right? Well, in this one, we're not going to divide by that number because A, B, and BA are different outcomes because A comes first, then B, B comes first, then A. In a permutation, order matters. So the formula for a permutation, so for permutation, I'm sure there's something like this for a permutation. I don't know. Anyways, would be n factorial. So we're talking about the number of items and then the number of ones that we're choosing from. Then we would just have n minus r factorial here that we need to divide out. So these are the things that we are not choosing. Those get divided out because we don't care which order those are in. So in this case, you can see that we've doubled our outcomes, our possible outcomes, because the order did matter. A, B, and BA are different, whereas in a combination, A, B wasn't different. It's the same thing. Or A, B, and BA aren't different. All right, so how can you tell if you're looking at a problem that needs a combination versus a problem that needs a permutation? So let's look at this first example. We've got 2 very similar problems here, but one is a combination and one's a permutation. So on your trip, you plan to go to 7 European countries. Okay, so there's 7 things. How many ways can you leave home and fly into one country and then return home from another country? All right, so I've got 7 countries. I'm going to leave and go into one and then come back home from another country. All right, that's our first one. On your trip, you plan to visit 2 of 7 French cities. How many different ways can this be done? All right, so in this one, we're still doing 7 items and picking 2, but one of them's a permutation and one of them's a combination. This first one is a permutation. Because let's say that I fly into France and I come home from Spain. So France, Spain, fly into France, come back from Spain. Well, if I flew into Spain and came back from France, that'd be a totally different trip. So order does matter in this one. So this one would be a permutation. So this would be a permutation where we have 7 things and we're picking 2. So the number of ways that we could do this would be 7 factorial over 7 minus 2 factorial, or 7 factorial over 5 factorial. These reduce, we get 7 times 6, 42 ways. So there's 42 ways if we're flying in, coming back home from 7 different countries, 42 ways. Next one, we're going to visit 2 of 7 French cities. Okay, so I got 7 French cities. Maybe I've got Paris and Lyon or something like that. So if I go to Paris and then Lyon, well, is kind of the same thing as going to Lyon then Paris. They're the same trip, basically. It doesn't matter which one I'm going to first. So this one is a combination. So in a combination, we can either write it as 7, 2, or 7 combination of 2. So in this one, the order doesn't matter. So when I do 7 factorial, I'm going to divide out the things that I am picking, the number of things I'm picking, because going to Paris and then Lyon is the same thing as going to Lyon and then Paris, because it's just how many countries, which countries am I visiting? The order isn't mattering. And then I have to take out the ones that I'm not picking, 7 minus 2 factorial. So we would get 7 factorial over 2 factorial, 5 factorial. The 7 and the 5 reduce again. I get 7 times 6. And then in the denominator, I still have the 2 from this 2 factorial here. That reduces to 3. I get 21. So we can see here that the combination had fewer outcomes than the permutation did. It's kind of funny that like a lock, we call it a combination lock, where you have like a combination that you put into the lock. That's not actually a combination. It's a permutation, because where you put in your code for your lock or whatever, the order matters. So technically they should be called permutation locks, but it doesn't roll off the tongue quite as well. All right, second one. Let's see if we can tell the difference between them. If there are 10 people in a social club, how many ways can you create a committee made up of the 3 members? Okay, so we got 10 people in the club. We're picking 3 of them for a committee. Other option, there's 10 people in a social club. Okay, same thing. How many ways can a president, vice president, and secretary be chosen from the members? All right, so I'm making a committee of 3 people. I'm choosing a president, vice president, and secretary. It's still 10 people picking 3. But in the second one, the order does matter. It matters who's the president. It matters who the vice president is. It matters who the secretary is. So if I've got Angus, Carl, and Gustav, it matters if Gustav is the president or if he's the vice president. So those 3 people can have different combinations. Well, actually 6 different combinations just from those 3 people. So having those 3 people would give us more combinations. So this one's our permutation. And this is our combination. So the combination was 10 pick 3 or 10C3. So we would do 10 factorial over 3 factorial, 7 factorial. the things we're picking, the things we're not picking. These reduce. I get 10 times 9 times 8. And then down here, I got 3 times 2. The 3 reduces with the 9. The 2 reduces with an 8. So I got 3 times 4, 12, times 10, 120. So there's 120 ways. So the next one is a permutation. We should get more than 120 ways to do it. So we would do the permutation of 10 things, picking 3. Now we're going to do 10 factorial over only 7 factorial, because these are the things that we're not picking. This would be 10 minus 7 factorial. No, 10 minus 3 factorial. All right, so we're not going to take out this, because remember, this portion is the 3 people that the order doesn't matter. We're taking out those combinations where they're repeated the 3 people. But in this one, we do want to repeat the people because the order matters for them. So I'd reduce the 10 and the 7. I'd get 10 times 8 times 9, times 9 times 8 left. 9 times 8 is 72. 72 times 10 is 720. So we see here that we have quite a few more combinations when we did it as a permutation. And that's always going to happen. Permutations, there's always more than a combination. Now, I would love it if all of your problems were this straightforward and simple. But sometimes you have unlimited items to choose from. And that really throws a little kink in your system. So like on this one, we had 10 people from, a social club. So there's 10 people. What if there was like unlimited number of people to choose from? Well, that kind of changes things. So it makes these problem solvings a little bit more difficult, and you have to think through the different cases or the different scenarios that might be possible. So here we got 3 buckets with bolts, screws, and nails. Okay, so they're filled with these things. I got a ton of bolts. I got a ton of screws. I got a ton of nails. So it's like I've got unlimited items. Now I'm going to pick 2 of the items. Well, here's my problem. This looks like it would be a 3-pick 2, but it's not. Because when we have a 3-pick 2, there are only 3 items total. But this one has multiples of each that I could choose. So a lot of times on these problems, I like to come up with the different cases, the different things that could happen. So I'm going to come up with 3 cases for this one. Case 1, case 2, and case 3. So what could happen in this? Well, I could get all 3 bolts, all 3 screws, or all 3 nails. So all bolts, so all of 1. So what if I get all of the bolts, all the screws, or all the nails? How many different combinations can I get when I'm picking 2 items? Well, I could get 2 bolts, or 2 screws, or 2 nails. So in this case, there's only 2 cases in this. So there are 3 different ways to do it if they're the same. However, if they're different, I'm only getting 1 of one and 1 of another. If they're different, then this would be a 3-pick 2 scenario. Oops, not a fraction. Dang it. So if I'm getting 1 of one, or 1 of 2 different types, so if I'm getting 1 of 2 different types, that would be a 3-pick 2 scenario, because I could do a bolt then a screw, or a bolt then a nail, or a screw then a nail. So that would be 3 different combinations, 3-pick 2. Which just comes out to 3. So I actually have 3 outcomes in case 1, and I have 3 outcomes in case 2. So that's a total of 6 outcomes. So there's 6 ways to do it. So you can see, because we had separate cases, we have different probabilities than just a simple, straightforward 3 pick 2. Because there were an unlimited number of each of these to do it. So we have to break up the different cases, and then, yeah, the more items that you have with unlimited things, the more ways that you have to split up the cases. So these are the types of problems you really have to think through, and think through all the different possibilities that might happen. All right, that's all I got for you today. Math hard. See you later. Bye-bye.